Jason Fuller. I'll be your host today. Welcome back to the PNNL Grid Resilience webinar series. In this series, we've been excited to share with you some of our current research efforts at PNNL that are addressing grid resilience, considering both climate change and the clean energy transitions. In our first session, we heard from some of our PNNL grid research experts discussing some of the challenges facing the grid, including some of the tools developed to support grid resilience through modeling. That was Jeff Daigle and myself. We have since had two sessions discussing local scale extremes. Our first talk discussed some of the wildfire research activities at PNNL, including utilization of remote sensing technologies and development of machine learning models to understand future wildlife behavior in a changing climate. Our second talk explored challenges with drought, and not just water availability and the impacts to energy systems, but other weather-related energy resources such as wind and solar. Today, we'll continue along the same theme of understanding how local scale extremes impact our power systems. Today, we'll focus our attention on resilience to hurricanes and floods. And our final session in 2 weeks will focus on exciting new research and tools that use to represent technology change in our energy system portfolio and what that means to overall grid resilience. And for today's topic, it will be my pleasure to introduce David Judy and Karthik Balaguru. Let me give you just a little bit of background on both of them first, and then we'll kick this webinar off. So Dr. David Judy has more than 20 years of experience in developing and applying modeling and simulation tools to quantify the response of human systems to extreme hazards, including natural and anthropogenic events. Within this research topic, Dr. Judy has become a nationally recognized expert in flood risk modeling and rapid response flood modeling. Dr. Judy joined PNNL in 2015, where he has been studying the effects of climate change on infrastructure systems and the development of approaches to evaluate system resilience. Prior to PNNL, he spent 9 years at Los Alamos National Laboratory as an R&D engineer in the Energy Infrastructure Group. Dr. Judy received his PhD, MS, and BS in Civil and Environmental Engineering from the University of Utah. Karthik Balaguru is an earth science scientist and team lead for the coastal modeling team at PNNL. He joined PNNL in 2011 after receiving his PhD in physical oceanography from Texas A&M University. Prior to this, he obtained an MS and BS in ocean engineering from the Indian Institute of Technology, Madras. Dr. Balaguru has a broad background in climate dynamics with expertise in upper ocean processes and air-sea interactions. He has worked extensively on the role of ocean stratification and mixing processes in tropical cyclones and the intersection of tropical cyclones and climate. More recently, he has also been leading efforts to better understand the resilience of human systems and infrastructure in coastal regions to extremes in a non-stationary climate. And with that, I will turn it over to Dave and Karthik to begin the presentation.
Thank you, Jason, for that introduction. I'm happy to be back here today, this time as a presenter. So I'm going to kick off with a little background, which some of you may already be familiar with, about the prevalence of tropical cyclones and floods. And we use tropical cyclone and hurricane a bit interchangeably here. Sometimes you'll see us say tropical cyclones or hurricanes, but we mean the same thing. Globally, tropical cyclones and floods are amongst the deadliest and costliest natural disasters that we see. I have a couple charts here taken from the World Meteorological Organization from some 2021 report where data had been collected over time. 17% of all the global disasters reported were tropical cyclones, but they caused 38% of the disaster-driven deaths and reported economic losses. So very significant, not just the number of times they occur, but the impact they have. 24% of the global disasters are coastal floods and cause about 20% of the economic losses that have been reported. So what regions in the world are most impacted by tropical cyclones? Well, it turns out there are a few specific regions. In the United States, Japan, and China account for about 73% of the tropical cyclone economic impact. In the US, on average, 1 to 2 hurricanes make landfall in the US each year. The chart here is again taken from the World Meteorological Organization, looking at regions within the world where tropical cyclones are impactful. So clearly the North America and down to Central America, Asia, and then the Southwest Pacific. So 3 of the top 10 global events occurred in just 1 year in 2017, and those were Harvey, Maria, and Irma. So looking a little closer here to home, and this is data taken from NOAA, looking at the prevalence of events since 1980, and there's no trend line here, but you can clearly see the number of events has been increasing, both for tropical cyclones and flooding. So a couple more charts from NOAA. This is looking at billion-dollar disasters. Some of you may have seen these before. So this is looking at 2020, which was a record year for billion-dollar disasters. 22 of those events. Several of these were hurricane and flood related. Notable events in 2020 included Hurricane Laura, which was about a $19 billion event with 42 deaths, and then Hurricane Sally, both of these occurring in the Gulf states. Looking at last year, it was the second most disastrous year for billion-dollar events, where there were 4 tropical cyclones and 2 other significant flood events. One event in particular that you may recall is Hurricane Ida, not just the actual hurricane itself, but the remnants of Ida. And so this had wide-ranging impacts from the Gulf, where it made landfall in Louisiana, and then the remnants of Ida, where it dumped a lot of rainfall in the Northeast, in particular, extending all the way from Philadelphia into Connecticut. This event had about $75 billion in damage and 96 deaths. So very recently, we've experienced a major event in the U.S., Hurricane Ian. Just within the last couple of weeks. Cost estimates are still pending, but sure to be another significant event with 100+ deaths in Florida. This was at last count, and final numbers aren't in there. This was a rapidly intensifying storm with substantial coastal and inland flooding, and Karthik's going to talk a little bit about the prevalence of rapidly intensifying storms here in just a second. This event had significant impacts to the electric power system. This is an image I grabbed from NASA on the left. It's looking at power on a normal day, the baseline conditions for power delivery. And on the right, looking at post-event, September 30th, just after the event happened in Fort Myers, Cape Coral region. So clearly a lot of electric power impacts, and I think the number was about 2.7 million people without power during this event. So Florida, like many locations in the US, are growing in population. I think the number is about 3 million people added to Florida since 2010. Hurricane Ian was an example. This is a graphic taken from CNN that I thought was quite interesting, looking at impervious surfaces in the area hardest hit. In 2001, you can see the impervious area, and then when it goes to 2019, a lot of that dark area has been filled in. This is something we're experiencing across the US and in the coastline areas, where more than 50% of the US population resides in those areas, and we continue to grow, putting themselves potentially in harm's way from these types of events. So with that background, I'll turn it to Karthik to talk a little bit about research we're doing with tropical cyclones.
Thank you, Dave. So I want to begin by drawing your attention to a recent study of ours, where we looked at how hurricanes have been intensifying in the nearshore region, close to the coast. So in the top left panel, we have track locations close to the coast that we considered in this analysis. So the magenta line roughly represents a distance of 200 nautical miles from the coast, which is the United Nations definition of near coastal. And then, so these data, tropical cyclone data, are directly obtained from the National Hurricane Center's HRDAT database. And what you can see in the top right panel are probability distributions of 24-hour intensification rates that we computed for hurricanes over the period from 1979 all the way up to 2018. So this is roughly the period during which hurricane observations are more reliable because of satellites. So over this period, what you'll see is, so the blue, the distribution in blue corresponds to the earlier period from 1979 to 98. And then the orange distribution corresponds to the later period from 98 all the way up to 2018. And what you'll see is, and the green is a difference, and you can see that the distributions have shifted towards the right in the more recent period compared to the earlier period. And this basically means that tropical cyclones have been intensifying more rapidly in the important nearshore region ahead of landfall. And this shift is pretty robust statistically. So once something like this happens, you would want to understand why this is happening. And for this, we looked at the large-scale environment through which the storm moves. And in the lower left panel, we have trends in the sea surface temperature. And the lower right panel, we have trends in the atmospheric humidity or moisture. So in general, what you'll see is the ocean is becoming more and more warm close to the coast. And also in the nearshore environment, the atmosphere is becoming more humid or more moist. And these changes in the large scale environment are certainly favorable and conducive for intensification close to the coast. And when you combine these changes in hurricanes with rising sea levels, which are also simultaneously happening, it really becomes very important for us to be able to not only evaluate the coastal hurricane risk, but also project it into the future. Next slide, please. So how do we quantify hurricane risk? The first thing you might ask is, how about observations? So as Dave mentioned earlier, there's roughly like 1 to 2 storms making landfall over continental US each year. And when you consider that the reliable hurricane record extends back 40, 50 years, and these number of observations are certainly not enough for robust risk assessment. So the next thing you can ask is, how about climate models? Now, the typical climate models operate at resolution of roughly 1 to 2 degrees. And at this resolution, these models can actually simulate the environment of the storm fairly well, as you saw in the previous slide. So to understand the environment, these models are very, very suitable. However, at this resolution, the models cannot simulate hurricanes directly. And then there are also high resolution climate models. So these are models that operate at a resolution of roughly 1/4 degree or even higher. And at this resolution, the models can explicitly resolve tropical cyclones. As an example, in this figure on the left, you see the simulation of an intense hurricane in the North Atlantic from E3SM, DOE's Earth System model. So while these models are good to understand changes in hurricane characteristics at the basin scale or the global scale, but that's not enough for a local scale impact, because you will have to simulate hundreds of thousands of years of simulations, and that is computationally very expensive. So to overcome these challenges, we developed the risk analysis framework for tropical cyclones, or RAFT, at PNNL. Next slide, please. So what is RAFT? So RAFT essentially is a hybrid model that combines physics, statistics, and machine learning to produce large ensembles of tropical cyclones. It is trained using observations and can accurately represent the salient features or characteristics of tropical cyclones. So the figure on the top right is a schematic that shows a high-level overview of RAFT. So it has basically 6 components. So 3 of them are related to the characteristics of storms themselves, which is the track, you have the along track intensity, and also rainfall along tracks. And once you have these 3 characteristics simulated, then you can combine them in various ways to look at different types of impacts. For instance, you can combine the track and intensity with a storm surge model to look at coastal flooding. You can combine your track and intensity again to look at impacts on electric infrastructure and so on. And also, you can use rainfall from storms to look at inland flooding. So this is how the different characteristics of RAFT can be combined to look at different types of impacts. So why is RAFT suitable for risk analysis? So there's a couple of reasons. So the first thing is the large numbers. So at a very, very low computational cost, RAFT can simulate large numbers of tropical cyclones, which allows robust risk assessment. And besides, beyond the large numbers, accuracy is very, very important especially for local scale risk assessment. And RAFT also does a good job when it comes to the spatial distribution of tracks. And finally, another important aspect of RAFT is its ability to project risk from hurricanes into the future. And we do this using climate models. And I will show examples of all of this as we go further. Next slide. So the first thing we do in RAFT is to generate tracks. And for this, we use a physics-based approach and what we call as a beta advection model. So here, storms are simply advected forward in time based on a weighted mean of winds in the upper and lower troposphere. And to this, we add a correction related to the rotation of Earth. So the figure on the left illustrates the typical steering flow in the Atlantic based on the advection based on the upper and lower winds in the atmosphere. So you can see that in general, to the south of 30 north, the winds, the steering flow is predominantly easterly or blows from east to west. So the storms that form in the main development region are carried west towards the coast. And then further north, the steering flow carries the storms away from the US coast. But the real strength of RAFT can be illustrated by this figure on the right that shows more than 1,000 storms passing through the vicinity of New York City. So you can literally pick any location along the coast and you can have hundreds of thousands of storms passing through it. And these large numbers allow robust risk assessment for that location. Next slide, please. So once you have the tracks, the next step is to generate intensity along tracks. And for this, we use a deep neural network based approach. And more specifically, we have a multi-layer perceptron model that is trained using the global environmental predictors that play a critical role in hurricane intensification. And these predictors are obtained from the National Hurricane Center's SHIPS database. And what we found is once we trained our model and we performed some benchmark tests, and we found that the intensity model, the neural network-based intensity model that we developed outperforms some of the well-known statistical dynamical models employed at NHC for operational forecasts. And once you have the intensity model, you can combine it with tracks to produce intensity along tracks. And what we found is RAFT produces a realistic distribution of intensities at the basin scale. And also it does a fairly good job of representing coastal hurricane risk as illustrated by these figures. So the figure in the bottom left shows the distribution of the lifetime maximum intensities for hurricanes in RAFT. And you can see that the storm that RAFT produces even intense hurricanes. By that, I mean major hurricanes with wind speed exceeding 100 knots. Now, this is an important aspect of RAFT, which is highly relevant for risk assessment. And in terms of the spatial distribution of risk, RAFT again does really well. So you can see from the two figures on the right, the top panel is from direct observations and bottom panel is from RAFT. And you can see that the coastal hurricane risk is well represented in RAFT compared to observations. So you can see that in general, some areas are projected to have more risk from hurricanes, such as over Florida, the Georgia coast, and the coast of Carolinas, and also in the northern Gulf Coast near Louisiana and parts of the Texas coast. Next slide, please. So once you have the track and intensity, the third thing we do is generate rainfall along tracks. And for this, we use, again, a physics-based approach. And in this, the tropical cyclone rainfall is simply estimated as the upward, the vapor flux above the boundary layer. And the vapor flux is simply the vertical velocity in the atmosphere times the saturation specific humidity. And this vertical velocity has 4 components. So it has the frictional effect, which is related to the roughness of the surface over which the storm is moving. And we have the vortex stretching effect. And we also have the topographic effect, which is related to whether the storm is moving over a hill or a valley and so on. And finally, we have the baroclinic effect, which is related to the environmental shear. So once we have these four components, we put them together and calculate the precipitation. So here we provide two examples to show how RAFT does when it comes to simulating rainfall from hurricanes. So the top two panels are for Hurricane Isabel from 2003, and the bottom two panels are for Hurricane Irene from 2011. On the left-hand side, you have direct observations of precipitation from satellites. And on the right-hand side, we have precipitation from RAFT. And you can see that despite some limitations, overall, there's a reasonable agreement between precipitation from RAFT when it comes to compared to observations. For instance, RAFT, the rainfall from RAFT is more homogeneous compared to observations. And also in terms of the magnitude, RAFT tends to slightly overestimate precipitation closer to the center of the track. However, despite these limitations, the overall agreement is reasonable between RAFT and observations. Next slide, please. So another important aspect of RAFT is its ability to project hurricane risk into the future. And for this, we combine RAFT with state-of-the-art climate models. So we have simulations of climate model corresponding to the historical period and the future period. And for each of these periods, we combine with RAFT to produce climatologies of tropical cyclones corresponding to those periods. And once you have this, you can look at the difference between the climatologies for the future period and the historical period. And then you can look at the difference, which will allow you to see how the hurricane risk will likely change into the future. So as an example of this, on the top right, you have the coastal hurricane risk from RAFT based on historical simulations of climate models. Again, you can see that the spatial distribution is in pretty good agreement with what we found in the observed. And in the bottom panel, we have the future change in the coastal hurricane risk projected by RAFT. And this future climate scenario that we picked here is called the SSP 585 scenario. SSP basically stands for a shared socio-economic pathway. And 8.5 represents the increase in the planetary radiative forcing due to greenhouse gases by the end of this century. So under this climate change scenario, you'll see that RAFT projects an increase in risk for much of the Gulf Coast and the lower East Coast up to the mid-Atlantic. So these regions will likely experience more hurricanes going into the future under this climate scenario. Next slide, please. So that was impacts at the basin scale. But the other nice thing you could do with RAFT is to zoom into regions and look at local scale impacts. For example, here we use the example of Puerto Rico to illustrate this. So in the top right panel, we have changes in hurricane frequency, which is how often hurricanes are encountered for this region. In the middle panel, we have changes in the distribution of intensity for storms passing through Puerto Rico. And the bottom panel, we have the translation speed or the forward moving speed for storms while they are over Puerto Rico, and for both the historical and the future periods. And you'll see that in general, for this particular region, RAFT projects an increase in frequency by nearly 30%. What that means is Puerto Rico will likely experience a higher frequency of hurricanes going into the future. And not just frequency, the more serious thing is related to the intensity, actually. So you'll see that RAFT projects an increase in intensity by nearly 26 knots on average, which roughly translates to 13 meters per second, or like several categories of difference. So that's when it comes to frequency and intensity. However, these changes could be slightly alleviated by changes in translation. So you can see that compared to the historical, in the future period, the translation speed is projected to increase, which basically means that storms would stay for a lesser time over Puerto Rico, and they would pass over that region faster going into the future. So this would slightly alleviate the impacts from frequency and intensity. So if you go to the next slide. So finally, I want to show that besides looking at risk into the future, we can also use information provided from RAFT regarding hurricane characteristics and how we can use that to assess impacts on human systems. And we'll illustrate this using the example of electric grid, again for Puerto Rico. So what we do is we generate a spatial wind field for hurricanes based on the track and intensity obtained from RAFT. And this wind field is realistic because it is asymmetric about the axis, and also it has other realistic features. So once we have this wind field, we can generate a wind gust corresponding to that field, which is a function of the height above the ground. And once we have the wind gusts, we can combine them with fragility curves for different material to look at the failure rates for infrastructure for hurricane winds. So again, this we illustrate using the example of Hurricane Maria in 2017, which was a devastating Category 5 hurricane that nearly wiped out Puerto Rico's electric grid. So the top panel here shows the track of Maria passing through Puerto Rico, and the color over the island shows the probability of failure for wooden infrastructure to Maria's winds. And you'll see that the storm entered the island near the southeast coast, and the region where it entered, the probability of failure was very high because the winds were very, very strong once it entered Puerto Rico. However, as the storm gradually moved westward, its winds decreased slightly, and because of due to interaction with land, and as a consequence of that, the failure rates also decreased as you go westward in the island. So when you look at the spatial distribution of these wood failure rates, they are in pretty good agreement with what actually happened during Maria, which much of the infrastructure impacts occurring in the eastern part of the island. So this is about impacts on human systems. But to continue this discussion and to talk us through flooding, I will hand it back to Dave at this point.
Thank you, Karthik. So yeah, thanks for that, passing it back here. So Karthik, this figure on the top right, Karthik already introduced, talking about the components of RAFT, particularly around track intensity of rainfall. So from an impact standpoint, we can look at wind and wind impacts like Karthik just talked about with electric power poles as an example. The other component is taking the precipitation and the wind and developing flood estimates. When we talk about tropical cyclones, we're really talking about multiple components of flooding. There's coastal flooding, and then two components related to inland flooding, both fluvial or riverine flooding, and then fluvial flooding, which can happen within your urban systems. And so when we talk about flood risk, the goal would really be able to capture all of those components. And sometimes they may compound. So rather than just superimposing one of those events on top of the other, they may actually have an interacting effect that may make the event actually worse. So with that in mind, I would talk about some tools that we've developed to be able to take these estimates of rainfall and wind and develop flood projections so that we can further look at coastal risk. So sorry to show a little workflow, but this is a generic workflow, and I want to draw your attention to this dashed line here. We can force, so we have a series of flood models that I'll talk about in just a minute. They can be forced with weather forecast data in an operational sense. So there's a pending event, we can take, for example, National Weather Service data, and I'll give some specifics on that. Or this framework for developing flood extents can be driven by a synthetic model such as RAF, where wind and precipitation estimates have been driven, and we can feed those into our modeling framework. The model I'm going to talk a little bit about is called RIFT, and so we have RIFT and RAF. RIFT, Rapid Infrastructure Flood Tool. We've been developing this for a long time, funded primarily out of DHS programs. It's a two-dimensional hydrodynamic model that uses some unique numerical techniques and computing resources to make it feasible to use the model in a kind of near real-time sense, but also to develop larger ensembles for probabilistic risk. So with the operational setting in mind, the tool was developed to ingest data sets that are readily available, such as topography that the USGS develops, and bathymetry, in addition to any of the weather products that are out there, being able to ingest it in there pretty readily. Initially, RIFT was developed with an operational context in mind, so supporting decision support around planning, response, recovery, and mitigation for events that are occurring, and providing insight for infrastructure owner operators, federal, state, local emergency operation centers. But these tools that we use in an operational setting are still applicable in a research setting where we might be asking risk questions around climate change, as an example. So RIFT, as I mentioned, was originally developed with an operational setting, and we're talking today in the context of tropical cyclones. I just want to mention that the tool itself is applicable to a wide variety of events. RIFT itself is really good at describing overland flow within complex topographic environments. So today it's relevant to extreme precipitation, so taking rainfall runoff from a model like RAF when you have precipitation during a hurricane, and estimating what the inland component is combined with coastal flooding. But the same tools are applicable to other types of events, for example, levee failure, which you might have happen as we saw during Hurricane Katrina in New Orleans with levee failure. And so the tool set is really usable across a wide range of events. So what are we trying to answer when we develop flood simulations? Well, there's a couple of core set of questions we're trying to answer. So primarily, what is the spatial extent of flooding? And also, what is the timing of the flooding? The timing is important from a planning and response perspective, but also from a recovery standpoint and understanding some of the longer term implications. So in that case, we might care about the flood arrival time or the dry time. But we also ask questions once we have that information about how many people are at risk and what infrastructure at risk. There's a number of ways that we can support that during actual events, and that is through predictive modeling and simulation, which is the RIFT tool set. We can also leverage existing simulations. So we maintain a repository of simulations that we've run in the past, and we may be able to leverage those to understand what an event might look like that's coming in the forecast. We also have some capabilities. We heard a little bit about a capability called radar a couple of weeks ago with respect to fire. That capability is also used around damage analytics during floods. So just a quick look at the types of output you get when we run these simulations. So primarily what we simulate are depth and velocity. And so, and this is resolved spatially and temporally. So we can get that temporal evolution, the spatial evolution, and capture flood depths and velocity in any region of the US. Some of the derivative products that you pull out of once you have depth and velocity, you're understanding, like I mentioned, flood dry time, which I mentioned has implications for recovery. It also could have implications for health impacts. And then flood wave arrival time. There's a number of other metrics that we use. So there's flood severity metrics we develop based on combinations of depth and velocity and other types of algorithms. So with that information, we can start understanding what the effects are, the consequences of an event. So We can look at population at risk using available data sets. We can estimate what loss of life would be, which takes into account the onset of the flood, how long it's there, the severity of the flood. But we can also start looking at infrastructure impacts. And this could mean general building stock, but also things like our electric power infrastructure, how many substations are impacted and how long will they be impacted? And what's the cascading effect of the loss of those substations? And then also looking at things like economic impact, business disruption, and so forth. So I'm going to just show two examples of how it's used here. So this is in an operational setting. So back to the same figure of looking at how we go through the process. So forcing the model with operational data sets. So from a precipitation forecast, taking National Weather Service products such as the quantitative precipitation forecast, or even radar observations to do a hindcast simulation. So that will cover the inland component. And then for the coastal component, a lot of times we're pulling in simulations that are already done out in the community, whether that's from the National Hurricane Center using SLOSH, or using the SARA ADCERT simulations, which are readily available to use also. And then using those to run a new simulation to capture all three components of flooding. So we've been using RIFT in this context for many years in the response community, and most recently it was used in Hurricane Ian to support response in Florida, both at kind of the federal and state level. This is an example out of Hurricane Florence a few years ago, and to give a sense for the timeline of simulations, generally we're looking at running simulations twice daily when there's an event, and making those available to stakeholders who are making decisions around how they should respond to an event. And we'll update those based on forecast changes. So what I want to end on here is talking about how we use that in a planning sense or risk analysis sense. So taking information, for example, from RAFT, and being able to look at the associated flooding impacts from a large ensemble of hurricane projections. So in this case, now I've modified the left side, and now we're looking at climate forcing. So Karthik presented a little bit how RAFT can be driven by GCMs. He showed a downscale looking at Puerto Rico in particular. And so out of these large ensembles, which can have climate projections in them, we take the synthetic tropical cyclone track and intensity. We can use the models like ADCERT, SLOSH, develop the storm surge information. But we can take that precipitation component out of RAFT and provide estimates of what the inland flooding component will look like too, to get at the three components of flooding that we care about: the pluvial, fluvial, and the coastal flooding. This is an example of doing that, and this is a synthetic tropical cyclone reminiscent of Irene. So this track is not exactly Irene. This was a track that was run through RAFT, generated intensities and precipitation that is reminiscent of Irene. And we took that information and ran that through. In this case, we use SLOSH, can also use ADCERT to generate the coastal component, and then use that as a boundary condition when we run our inland simulations using RIFT, in this case looking near Wilmington, North Carolina. As a proxy to look at the nonlinear effects of when we include compounding effects, when we include just rain-driven floods or the inland floods, there was 19,000 people affected. When we included just the coastal effect, the surge, there were 14,000 people affected. But when we look at the compounding effect, it's actually nonlinear. Those don't quite add up. There's some interacting effects which we're interested in from a risk standpoint and making sure we capture. So this type of analysis can be repeated over large ensembles, with each of the tracks, intensities, and precipitation ensemble members having a probability associated with them, and then we can translate that to a flood extent. So in summary, Karthik provided some insights to a tool that we're using to generate large ensembles of hurricanes that not only allow us to look at risk, but also start to understand some of the changes we might see as we look towards the future with climate change. So I presented a little bit about how we can take those projections and develop flood estimates. and not just use the flood estimates to look at impacts, but we also talked a little bit about how we can take the wind estimates and look at wind-driven damages, for example, to the electric power system. So with that, I'll turn it back to Jason.
Thank you, Dave. And we do have some time here to start to answer some questions. Please go ahead and post those questions in the chat window here. If we run out of time and can't answer all the questions, we'll do our best to continue to answer them offline or through the chat afterwards. But to kick us off here, what can you say about with the confidence, or how confident are you about changes in track intensity and location in the future? That question is probably for Karthik.
Yeah. So so there are like different aspects to a storm related to impacts. So there are like frequency, intensity, and rainfall, or how wet the storms are. So when it comes to, first of all, frequency, we don't have really a consensus. So the community is divided with some studies projecting an increase and some studies projecting a decrease. There is no like a unanimous agreement among the scientists when it comes to frequency. However, when it comes to intensity and rainfall, there's an overwhelming consensus. So in general, storms are projected to become stronger, and they will also become more wetter going into the future. And so when it comes to intensity, as I showed in one of the slides, that one of the things that plays a role is the warming of the ocean, which is where the hurricanes derive their energy from. So when the oceans warm, the hurricanes will become more intense. And when it comes to flooding, as one of the things with climate change is that as the atmosphere warms, it will also have a higher ability to hold moisture. And this combined with the rate of intensification, when that increases, you have a lot more rainfall from storms. So, yeah.
Excellent, thank you. And with some of the projected changes in hurricane intensity, do we expect to see increases in flooding, both coastal and inland?
Yeah, again, to this, partly because, I mean, flooding can occur due to several reasons. So one thing is because of the storms themselves. So you have an increase in intensity, and also you also have more rainfall coming down from storms. So the important thing is, along with this, you have sea level rise happening near the coast. And when you factor the sea level rise also, then it would cause more flooding in the coastal region once the storm moves ashore.
And if I might add to that, I alluded to this in the beginning with Hurricane Ian and population growth. So flooding is likely to increase as we see increased precipitation, but another aspect of that is increased flooding, but also increased impacts as we continue to develop out in coastal environments or other flood-prone regions, which we're seeing consistently across the U.S. And so there's other contributions to risk increases in addition to the natural systems changing. There's changes in our human system which are driving up some of that risk.
Excellent, thank you. Thinking about some of the investments that utilities and others might need to make in this area, how can the hurricane and flood tools be used to inform energy investment decisions both today and maybe even looking well into the future?
Yeah, a couple of thoughts on that. One is we talked a little bit about risk analysis today and developing large ensembles. So RAFT in particular is a great tool to develop large ensembles, and you can associate probabilities with those and look at risk. And so from a decision standpoint, you can evaluate how much risk you're willing to take on relative to how you might harden your systems, or whether that's elevating or protecting and so forth. Another aspect that I think is interesting, I showed this a little bit with a storm track reminiscent of Irene, and also with what Karthik showed with Maria. In the community, there's increasing interest in taking storyline approaches, which is kind of a scenario-based approach, where you take events that we're familiar with, that we experienced, or maybe events similar to that, and then maybe run the storm that was. So, for example, Hurricane Maria, take the storm that was and look at how you respond and how you invest in your infrastructure, and then perturb that a bit and look at how a future storm would look like. So a future Hurricane Maria. And so this is something that we're seeing used more often now in providing context to stakeholders and how they might make decisions. Karthik, do you have anything you want to add to that?
Sure. I just want to add that when it comes to risk assessment, especially at local scale, a lot of times we are limited by sample size, especially when we use observations and even some of the models. Now, this is where a tool like Raft can make a real impact, because for local scale assessment, you need very, very large ensembles, and the size should be sufficient for you to be able to zoom into virtually any location of your choice. And a tool like Raft provides this at a relatively low computational cost. And the other nice thing about Raft is it doesn't rely purely on statistics and machine learning. It has strong physical underpinnings also. So because of that, it also increases your confidence in the tool when you are projecting risk into the future. Because sometimes when you use statistical models or pure machine learning based models, what happens is those relationships which are derived over the historical period, one would wonder whether the same thing would apply in a future period. However, if there is physics involved, that would lead to higher confidence in the application of the tool to not just the current climate, but also potentially a future climate.
Great, excellent. And a question about investment decision making. So if utilities will be using these models for investment decision making, of course, it'll first need to be blessed by regulators. Where are we today when it comes to regulatory adoption of these models and practices?
Good question. I don't know if I have a solid answer for that, since I'm not involved in any of the regulatory aspects. We are working with utilities and other organizations to at first level educate on what's available and how it might be used, understanding what's available in climate information, what's appropriate to use and what's not appropriate to use. But I think that's a good question, and I don't know if I have a great answer for how it's being adopted from a regulatory standpoint.
Thanks, Dave. What is done post-event to compare actual impacts to predicted impacts to infrastructure? Have you noticed any improvement in resilience over time due to new innovations?
Yeah, so we're not an organization that collects data, but there's a lot of organizations that do. For example, after an event from a flood perspective, FEMA mission assigns agencies to go collect, for example, high water marks and such. And that information is used to understand how models perform in projecting impacts. From an infrastructure damage standpoint, I know there's a lot of information collected on the, for example, electric power infrastructure side. So damage to these infrastructure system, number of people without power that are then fed back into models from a projection standpoint. I don't have great insight to how that's been used to improve resilience over time with the stakeholders. But I do know a lot of that information is collected by various organizations and shared from the infrastructure side.
Excellent, thank you. And this is really, really great applied research to see. What's next? Where can we take this work and tools? Is there new science that can be incorporated? Is there investments that can be made to improve these tools? Validation, kind of where do we go from here?
Karthik, you want to go first, or I can go first and then you?
Yeah, I'll probably quickly respond to that. So, so the data set, as Dave probably mentioned earlier, that we generate with Raft is pretty rich. So we can look at all types of analysis that are sometimes not possible with typical models and observations. So we want to look at more aspects of tropical cyclones and how they are changing. So I only showed one of them, which is related to how hurricanes have been intensifying close to the coast. But we will also look at other aspects of hurricanes that play a role in their impacts, such as, for example, how the rainfall from tropical cyclones will likely change in future and so on. So this is only like a snapshot of what is possible with Raft. We're definitely planning to do a lot more analysis. And also, I just want to mention that we're currently working on like a couple of manuscripts based on Raft. And once those manuscripts are published, the data would also be made available to the public, so people can dive in and do their own analysis with the data. Right.
Yeah, I might add a few things. Karthik talked some of the I guess science advancements that are kind of next too. There's a few of those things that we're working on. I mentioned a little bit compound flooding. That's something we're still working on and looking at interaction effects. We're tackling research around urbanization through various projects, in particular with the Office of Science, the Department of Energy Office of Science, looking at the role urbanization has in coastal risk when we look at that. And so that's some emerging research and developing projections of how coastal urban environments may look. But then I think as a nation, we're in a unique spot right now, and there's a lot of opportunity as we invest in new energy systems, clean energy systems, and making data available. We had a question about regulatory facts. There's a need for information right now around climate risks. And so I think one of the next important steps for us is to make sure information that's conducted within science communities can be used to help inform decisions around some of the applied areas and actual investment decisions. So one, how do we provide additional confidence in simulation results as they're provided? How do we communicate those uncertainties associated with them and make decisions around some of those uncertainties? So I think those are some of the high level opportunities that we have as we move forward.
Great, thank you, Dave and Karthik, appreciate it. I think we're at the end of our questions here. So I think if you hit the next slide, Dave, I believe we're going to wrap up this Q&A session here. We do have another session coming up here in about 2 weeks, or exactly 2 weeks actually. We'll have Gokul and Jenny talking about resilience to energy supply and demand changes, looking at future technologies and understanding how we incorporate those into a future energy scenario. I want to again thank Dave and Karthik for your time and appreciate your presentation today. And I appreciate everybody here attending, and please join us for our next series, next line series in 2 weeks. Thanks everybody.